We start again. So, yeah, last session we ended up here, right? So we ended up doing the stochastic gradient descent. And the difference with the full batch gradient descent was that we're not using the whole batch of data for training. So what was the idea of full batch training? So if I want to do full batch training, say with 60,000 images, for one iteration, how many times should I do forward, backward? 60,000, exactly. So I need to go over the whole batch of data that I have, meaning that I should just start with the first image, go forward, backward, second image, forward, backward, till the last one. So that was the idea of full batch training, and we said that full batch training is not a feasible approach in practice, because in practice it's going to be too complex to do, especially that you want to do so many iterations. So the alternative approach was that we go for stochastic gradient descent. So it was an alternative approach. And the simple version we talked about it was sample level stochastic gradient descent. So what was that? So if I want to do one iteration, how many forward, backward do I do? One, yeah? So I start with the first guy in the data set, I go forward, backward, I finish it, then I do the update, I go for the next one, and so on. So there was obviously less computation when I do a stochastic gradient descent sample level. I mean, I'm going to be much, much faster. But what is the price I'm paying if I do a stochastic gradient descent? Variance, yes, accuracy of my estimation, or the variance of my estimation. So the variance is the price that I'm going to pay, and we talk about this kind of trade-off that we have, the complexity accuracy trade-off. So if we do a stochastic, say for example we spend t time, or the amount of time we spend is t seconds to just do complete forward backward computation, okay? And then if I want to do just one iteration with the full batch, I need b times t seconds. Whereas if I want to do sample level stochastic gradient descent, t seconds is enough to just finish one iteration. So this is the complexity gain that I'm going to get using a stochastic gradient descent, but I'm going to have higher variance in my estimation. So we said every single of those gradients that we calculate in a forward, backward pass, we can look at it as a kind of estimator of a true gradient, the true gradient with this gradient of the loss, risk function that we don't have access to. So we can think of it as a kind of unbiased estimator, and then the variance of this estimation is going to drop by the number of samples we use. So we have b times more variance when we use a stochastic gradient descent as in compared with the full batch training. So this was the idea, and then we concluded this whole discussion, but by this last point that we can actually make a sort of trade-off between these two. So we can make a sort of trade-off between these two by just introducing the concept of mini batches. So what we do basically do with mini batch stochastic gradient descent, we consider the whole data set. We don't just do it sample-wise, because we know that it's going to have very high variance. But at the same time, we're not going over the whole batch in order to one iteration. So we are going to just break our data set into mini batches of order, say 100 samples. And then we start with the first mini batch. We go 100 times forward, backward. We compute the average, which is going to give us an estimator. This one is better than the sample-wise, is worse than the full batch, right? But then we use that one to do one iteration. Then for the next one, we go for the next mini batch, and we keep on going till we are over with our data set. And whenever we are over with our data set, we're going to shuffle everything randomly, and then we're going to start again from beginning, the first mini batch, and we keep on going till the end, right? So this is what we call it mini batch stochastic gradient descent, or mini batch SGD. This is the version that you know. Like nowadays, everybody says, like, we are going to use SGD to train this neural network. This is the one, because you always need to specify the size of your mini batch in that. So if I want to just write down the algorithm, this is basically the stochastic gradient descent we had, the normalized GDU with sample level update. The only difference is that we now loop over a mini batch, not the full batch, a mini batch. So how can I do it? Say I start with some weights, so some initial values for weights. I do a random shuffling at the very beginning. So I get my whole data set. It had, I don't know, 6,000 images. I just randomly shuffle them, right? Randomly permute them. And when I did that, I start to just break it down into mini batches. So I consider the size of mini batch to be omega. Then how many mini batches do I have? If I have b different data points, b divided by omega, right? So we have b divided by omega different mini batches. So this is the amount of mini batches we have. And then we start with the first mini batch. So what we're going to do when we get into the first mini batch, we're going to just do forward, backward pass for every single data point inside that mini batch, right? And then once we are over with all of them, we are going to just update or estimate the gradient by averaging all of those sample gradients we computed in this mini batch. Yep. And then we do one update of a stochastic gradient descent. We go for the next mini batch, right? So this is going to be the next mini batch. And we keep on going till all the mini batches are over. Now say I'm over with the whole mini batches, and I want to do one extra iteration. What should I do? I start again with the first mini batch, but before doing that, I should shuffle, right? So to just keep everything stochastic. So the only thing that I'm going to do is to just randomly shuffle. When I am completely over with my whole data set, I am going to shuffle everything again make mini batches, and again I start with the first mini batch and go over the whole data set. Clear? And I keep on doing this till I converge. So everybody's clear? Yeah?
I didn't understand why we need this gamma to increase during the time. Yeah, exactly.
Omega?
No.
This one.
Yeah.
This is the index of mini batch. So you have your whole batch of data. So you have, this is data number 1, for example, data number 2. These are the data samples that you have till B. And then what you do, you're going to collect a bunch of them. So this is omega of them. You put it in the first mini batch. So this is the length. In the first mini batch, then you have your second mini batch, and so on to your last mini batch, right? And then by that z that you see there, so by that z, I simply mean the index of this mini batch. So this is index 1. So you're going to compute your gradient over that. I mean, for every single point you do forward, backward. Once you compute it, you average all of them. So it's going to be your gradient, you update. Then you add z, so you're going to go for the next mini batch. Again, you update. And you keep on going till your last one. So now the last one is actually that capital Z that I have written there.
Where we save this gradient in this algorithm?
Sorry?
Where we save this gradient?
Here. Over. Each time I go over forward, backward, I compute one of them, right? And then I just average all of them that I computed. I just update, and once I update, I go for the next one, right? So I don't need it anymore in the next iteration, because for that one, I just use gradient of this one, right? So, any questions on that? Everybody's clear? So, that is, as I told you, the stochastic gradient descent, the mini batch version. This is the famous one which you use. There are a bunch of things that people, first of all, if here in this algorithm, if I put this omega, the size of every mini batch, to be exactly b, the size of my data set, my batch size, my full batch size, what would be this algorithm then? This is the full batch training, right? So if I put omega to be b, this is full batch training. If I put omega to be 1, what it should be? The sample-wise, right? So sample level, a stochastic gradient descent is the special case Full batch training is a special case, so it's a kind of more general training loop. This is one thing, and of course you can come up with the same trade-off, but the key point here in this trade-off is that you can now modify this trade-off. So if you consider, say, omega to be the size of your mini batch, then again, if you assume that t is the amount of time you spend for one forward-backward propagation, then the time that you spend with mini batch stochastic gradient descent is going to be omega times t, and then the variance is going to be the basic variance divided by omega, right? So again, you have this trade-off, but now you can play around with the trade-off, right? So you increase omega, you get better accuracy, less variance, but you need to spend more time, right? And you want to be faster, you can reduce omega, but this is going to be at the cost of higher variance in your estimation. Clear? Yes?
Oh, I have a question regarding the last slide.
This one?
Yes. So I'm kind of confused why we go back to line number 5 after line 14. Shouldn't we go back to like line number 9?
Yes, we go. We only get into 5 if omega passes the maximum number of mini batches we have. So you start first one, second one, till last one. When it's over, you need to again start, right? But you need to shuffle.
That's right.
Yeah. Okay, so any question? Clear? Good, great. So now you can think of this trade-off in form of such a curve. I mean, of course, this is not a kind of, specific evaluated curve. This is a kind of, visualization of the idea. So when you are using sample level stochastic gradient descent, you're basically having very high variance, but you're spending less time, right? Low complexity. If you do full batch training, then you're spending lots of time, but you have much less variance in your estimation. And the key point about this mini batch is that it lets you just move between these 2 points, right? So if you want to have, say, less time, you can just increase the variance by reducing that mini batch size. And you can, of course, get at higher complexity, and you just reduce the variance, right? So it depends on your design. And again, this is a kind of parameter you need to tune, right? It depends on the computation power that you have, also the amount of accuracy that you want, lots of things, right? So that is the idea. And of course, you see here that mini batch size, the size of your mini batch is the one which is drawing this trade-off, right? Okay, clear. Now, there are a few definitions. Probably all of you already know about that, but just to make it clear for everyone, something we call it batch size, which is basically the size of mini batch. So as I told you, many people already called mini batch to be batch, because at some point people somehow started to forget this fact that batch used to be called for the training set. Okay, so if you see like many texts, they're going to call the full batch of data either full batch or training data set, and then they call mini batches batch, which is a bit confusing for me at least, because I like that term mini. But usually, I mean, they call this size of mini batch batch size. Like at least when you use PyTorch, the keyword for that is batch size. Okay? So from now on, whenever I say batch size, I basically mean the size of mini batch. And if I want to talk about the full batch size, I either would say full batch or the training data set. So this is the batch size, basically that omega, the size of every single mini batch that you are considering. There is something called iteration. You basically know what is iteration. That is the iteration of stochastic gradient descent. Okay? So after every single mini batch computation, you do one iteration, right? Now, if I want to finish with all the data in the data set, how many, just look at the board, how many iterations should I do? B divided by omega, which we show it by z. Okay? So the number of mini batches that you have, you need to do that much iterations till you are completely over with your data set. And if you increase the number of iterations after that, you're going to get back here and repeat that, right? So this is what we call it iteration. So after each mini batch computation, you do one iteration, and then there is something called epoch. Epoch is basically when you are complete with your data set, meaning that you went over the first mini batch, second mini batch, third mini batch, till the last one. Now you're finished with one epoch. Again, you go for the next iteration, which is going to be the next epoch you start, and then you do exactly as much mini batch as you have, iterations more to finish with your second epoch. Clear? So epoch is when you are completely over your data set. Iteration is simply the iteration of your gradient descent algorithm. Clear? Yeah.
So just, in all cases, you're still going over the entire sample and trying to find gradients.
Of course, yeah.
So where do we actually gain in terms of computational intensity?
Because if you want to do full batch, each epoch that you do just one iteration, right?
You do the update.
Just one update, exactly. One update of the weights.
But then in full batch, you still have to compute all the gradients, average the gradient, and then do the update.
Exactly. And then when you are completely over with the whole epoch, no, in the stochastic gradient descent, when you over with one epoch, you already have done maybe hundreds of iterations. Because you do the iteration after every single mini batch, right? I'm going to give you a numerical example. But say here you have 100 samples in every single mini batch, okay? 100 over, you do one iteration, right? The second 100 is over, you do your second iteration. The second update, exactly. So if this is Amni's data set with 100 batch size, then you have 600 iterations to just be over with one epoch, right? So once you are completely over your whole data set, you already have done 600 iterations. Meaning that starting from this point, you have moved 600 times towards the minimizer of your loss function. Whereas in full batch, you don't move. You wait till you are completely over with the whole 60,000 samples, and then you move once. And the only gain that you get is that your gradient is more accurate. But let it be. Just let's move a bit.
So about how many times we can update for, like we can update in one iteration versus like the actual accuracy of the gradient. You're saying because we're splitting up into mini batches, we converge faster. Is that the?
Exactly. Because you need a certain amount of iterations for your gradient descent to converge, right? Because you are just moving with specific step size, right? So you need, say, for example, 1,000 iterations to converge. But if you do it in that way, then how many times you need to go over your data set? 2 times, 2 epochs, right? Whereas in full batch training, you need to do it like 1,000 epochs, right? Clear? So everybody's clear about this definition, batch, iteration, and epoch? Yeah.
Something question. I was wondering, for example, when we use some data set as a mini batch, can we again put them into our data set and again use another and shuffle them again? And
This is what we do, of course.
yeah, that's
So look, you get your whole samples,
yeah.
You divide them into mini batches. You go over all of it.
Yeah.
Then when the epoch is over, you again start from here, right? But before doing it, you just shuffle, yeah? But of course, one sample is being used as much as epochs that you're doing. So if you do 10 epochs of training, then one sample is used 10 times in your training loop.
I was wondering, for example, during an epoch, when we use the first mini batch, again we get it into it and try to shuffle them during one epoch.
No, that doesn't make any change. Because the only reason that you are doing the shuffling is because you want that in the next epoch you don't start with the same order so that you don't see that potential repetition in the behavior. This is the only reason. But once you're in one epoch, you don't care. Yeah. So, any questions? Great. So, now, if you look at this algorithm once again that we had before, now if we want to first of all specify where is the batch size, can you tell me which guy in this algorithm is the batch size? the omega, right? So that guy is a batch size. When you get into a mini batch, then you go that much times forward, backward, right? So in every single iteration that you do, you just go as much as batch size that you have forward, backward over your neural network. Once you are finished with that forward, backward, then you're going to do one iteration, right? So it's going to be one iteration, meaning that you update your weights once, right? This is one iteration of the gradient descent. Clear? And then the epoch is whenever you are finished with your data set, right? So once you're completely over with the whole mini batches inside your data set, then you start over, and then you're just starting with the next epoch. Clear? So now, let's just have one numerical example. Say we are just dealing with MNIST data set, which has 60K different samples, and say we want to just do mini batch stochastic gradient descent, and our batch size is 100. Okay, first of all, how many mini batches we have? 600. Because 60,000 samples divided by 100 sample per mini batch, going to be 600 mini batches, right? Now, if I start with my first epoch, how many iterations do I do till I finish that? 600 iterations, right? So you could say that when you start with your first epoch, you just have 600 mini batches. Each iteration you go over one of them, so you're going to have 600 iterations till you are over with your first epoch, right? And then after that, if you want to do more epochs, you're going to start over with your data set, right? So now, if I just do 10 epochs, how many total iterations I have done in my gradient descent? 6,000, right? Because in every single epoch, I do 600 iterations, right? And then in total, I'm doing 6,000 gradient descent iterations. Clear? Great. Okay, so that was the idea of this chapter is about when we are over with training. So now what you have learned is that if I give you one neural network, one basic neural network, MLP, then you can simply write down, specify the loss function. You get your data set, you break it down into mini batches, you use a stochastic gradient descent, and you train it. Say you have done the training and the training is over. Then what? I mean, how you can verify whether you have done a good job or not. And this is the part where you do inference, or you do the testing of your neural network. So what you want to do, at the end of the day, you're going to test whether this neural network is doing what you want it or not. Meaning that if I give you a new data point, say I give you a new image, we were talking about MNIST, right? So I give you a new image of a handwritten digit, you're going to give it to your neural network, you're going to check the output. The output is a vector of probabilities, right? Because it's output of the softmax, you remember that. Clear? And then you're going to compute the output of the softmax, you're going to take the maximum value, you would say this is what my neural network detects as the digit in that image, right? And then what you wish is that that thing that neural network after training is giving you is exactly the thing that is the true number on the image, right? So if it's a handwritten 0, you want that the output of your neural network has its maximum probability at the first entry, right? First class. So this is going to be the testing. And if you want to make sure that you have done the right training or your training has gone well, then you need to just try it for some test data set. But the key point is that the test data points or the test samples that you're using, they cannot be from your training data set, right? Because you already have trained over that. So you already have made this neural network to give you back very low error, very high accuracy output for those data points. Yeah? Now you want to make sure that if there is a new data point, which was not inside your training data set, that guy also passes through this exam, right? So this is why I told you initially that you are going to separate your data set, divide it into two parts. One part is the training data set, the full batch that you go over to train, And then you need a handful amount of data to just test your data set over them. And your neural network should have no idea about those data points before you start testing them. Clear? So this is the idea of testing. So what you're going to do, like in MNIST, you have 70,000 images. You're going to keep 10,000 aside. You don't use it at all. You just train your neural network on the other 60,000. And then once it's over, you start with those 10,000. You send the first guy over the neural network. You check the output, compare it to the true label. Again, you send the second guy. You compute the output. You compare it to the true label. And you keep on doing till you are over with all the 10,000 samples. Okay? Then what you can compute the test risk or empirical test risk, as well as the test accuracy. Now, what are these two? So test risk is simply you get your loss function, you check the output of your neural network, you compare it to the true label using the loss function you used to do the training, and you write down that value. This is the test loss. Okay? And then you have test accuracy. And what is that test accuracy? So you're going to infer with your neural network. So you're going to specify the output of your neural network, take the maximum probability. You say this is the class my neural network has found. Compare it to your true label. If it is true, then there is like 1. Yeah? You just got the accuracy 1. If it is false, then you got the accuracy 0. Yeah? They are not the same. And then you're going to average over all of these test data sets. So this is the idea that you're going to do. So you are going to just go over this test data set. And then for every single data point inside that, you are going to compute the test loss and also the test accuracy. And then finally, when you are over the 10,000 images, you just average it over all of the test guys. And then you're going to see how does your neural network works on this new data set. Okay, this new data points. So then what you're going to get as the test accuracy is definitely one number between 0 and 1, right? Because it is the fraction of times your neural network is working fine. So test accuracy could be 0.99, for example, yeah? Or it could be 0.58. Some number between 0 and 1, right? And the loss that you get is a kind of loss that you are of the same nature of the loss that you have computed for training. For example, if you have used cross entropy, it should be of the order of or of the nature of a cross entropy. So you hope that this is something close to 0, yeah, or even MSE. So now, you might tell me, okay, if we do that, so say we have trained our neural network, we passed test data points, and then we computed accuracy and the test loss or test risk, then these are two numbers, but usually when you look at textbooks, anything, you always see curves, right? You see curves. Now, there is one curve going up, one curve going down. So what are those curves? These are things that we call it learning curves, yeah? And this is not simply because we want to just show off some curve, right? The main reason for that is because we are not able really in practice to let the stochastic gradient descent or the gradient descent algorithm just converge. Because if you remember, when we started with the gradient descent, we said converging means that we need to just iterate as much as possible till the empirical risk is not going to change, right? And it might be billions of iterations or even more than that. Yeah? So it might be like trillions, I don't know what is the number, 10 to the power 25 iterations you might need, okay? But this is not really needed to be done, okay? So what we do in practice we do it this way. So every epoch that we are over, so we started with our first data mini batch, we've gone over the whole mini batches, we are over, one epoch is gone, so we have done multiple iterations. Now we are going to test our neural network. Okay? Give all of those 10,000 images, compute the test loss and test accuracy. You see it is not good. Test accuracy is, for example, 0.5. So 50% of the time it's still doing mistake. You do another epoch, right? Next time again you compute it. then it is, for example, 0.7. You say it's better, but it's still not enough. And you keep on repeating this. So you do more iteration, and after each iteration, or maybe after each couple of iterations, you're going to test your neural network once. And then you stop once you see that the accuracy you want is achieved. Clear? So this way, you don't really need to wait till the gradient descent, the original gradient descent, to converge, but rather you do it for a fixed amount of epochs. So this is now making sense. I mean, it's quite similar to what you hear outside, like they say, okay, we have trained this neural network for, I don't know, 50 epochs. Yeah? Meaning that by experience, they found out that 50 epochs is going to give them the test accuracy that they want. So they stopped after 50 epochs. Okay? You got the idea? So this is what we call it learning curve. So basically, if you plot that curve of the test accuracy and test loss after each epoch, you're going to see a sort of curve which is showing you what is the accuracy after each epoch finished in training, right? And then once this curve touches the point that you want, you stop the training. Everybody's clear? Any questions? Cool. So if you got no question, let's just do the example of MNIST so that we just recap everything we did. So say we want to just train this neural network, which we started this chapter with, to just do the classification over MNIST. So in MNIST, as I told you, we have 60K data points. These are for training. And we keep 10K other data points aside for testing. Okay? So what I'm going to do, I'm going to use cross entropy as we just did it in the lecture. And of course, we have 10 different classes for classification because MNIST has digits 0, 1, 2, till 9. Right? Now, say I'm going to use a mini batch stochastic gradient descent with batch size 100, and I want to do 100 epochs. So I'm going to get my data set, which is 60,000 images. I just break it down into mini batches of size 100. Now I have 600 of them. And for every single epoch that I start, I go 600 iterations, right? In each iteration, I'm finishing with one mini batch, correct? Now, once it's over, then in the very last iteration of my epoch, meaning that when I'm in the first epoch at iteration 600, I am going to just pass forward every test data points that I have, and I check what is the accuracy of this neural network right now. I'm going to record it. Then I go for the next epoch. I do the same thing. I again record the test accuracy. And I keep on doing it till I'm completely over with my 100 epochs. And then finally, what I'm going to show you, I'm going to plot that curve of test accuracy versus the number of epochs that I have done. And if we do it on normal data set, for test loss, it's going to be like this because it's obvious. Initially, when you start, you have not trained your neural network. So in the very first epoch, it's very bad. It gives you very high loss. But gradually after, each epoch is getting better and better, right? So it's going to return smaller and smaller test losses, right? And then you're going to just drop down, and it somehow saturates after some specific number of epochs. This is the point where you understand that even if I go beyond that number of epochs, I'm not going to gain that much, right? And then the test accuracy is going to look like this, right? Always bounded by 1, because you cannot have accuracy better than 1, obviously. And then initially, it's going to give you bad accuracy, maybe 20%, I don't know, 40%. But gradually, it's going to improve, right? So after first epoch, it's going to be 40%. Second epoch, it's going to be 60%. And so on. At some point, again, it's going to saturate. Yeah? So it's going to be very tiny changes. Like this epoch, it is 95%. Next epoch is 95.01%, and so on. Yeah? And then at that point, you're going to understand that, OK, if I, instead of 100 epochs, I go for 1,000 epochs, I'm not going to gain that much. So I'm going to stop it here. Yeah? But if you want to leave your gradient descent to stop when you see no change in the value of empirical loss, This pretty much never ends. Okay? So you got the point? Now, that's it for training and testing of a neural network, and this is the whole thing that we're going to do for every single architecture. So this was a simple architecture, fit for one neural network. More complicated architecture, we do the same thing, but with more complications, of course. Okay, any questions? Yep.
I was just thinking about the loss function that we use, so the cross-entropy loss. So from my sense is that we use it sort of the probability that something is a certain value.
Yes?
If we're, let's say, doing a neural network that's, let's say, predictive, like we're getting a value, but it's not that it's supposed to be one of a value, it could be sort of an infinite continuum. Would the cross-entropy loss necessarily be a good one?
You mean the
Like the output of the network, let's say it's giving...
like in the regression problem?
Yeah, something like that.
I mean, it depends on the nature of the output, but usually we don't do that. I mean, we usually in that case use MSE.
Just the mean square.
Yes, mean square error. But you can define it might be, because like in the binary classification case, also that y that you get is something continuous between 0 and 1. And you still can interpret it as a probability, and you can compute that thing, right? So it depends whether you are looking at it as something specific or not. I mean, it might be some other thing which, I mean, neither MSE nor cross entropy is useful. You just come up with your own loss function. So it depends on the application. So so what we learned here, first of all, the first message of this chapter is that backpropagation is an important and good thing, right? We all agree on that. Okay, cool. And then you basically always can do backpropagation on any architecture using the computation graph. And we talked about how we can do classification. In the classification, we just got rid of the issues of having partial derivatives and computing those gradients by interpreting those outputs as probabilities. And finally, we had the stochastic gradient descent, which we saw that the perfect one is the full batch, but we cannot really do it. So what we do in practice, we just use mini batches, and then we do a stochastic gradient descent over them. Okay? So that's it. Yes?
Yeah. When we are going multiple times during our epoch, I was wondering, doesn't our model getting overfit?
We are going to talk about that. Yes, you can potentially get, and we have some tricks to get rid of that. But of course, I mean, this is one challenge that you should, this is one of the things that you do that testing, right? Because when you test, you're going to somehow monitor whenever you get overfit.
The testing which we speak about is about our testing of the input data, the learning data. Am I right?
Not the training one, the testing one. Yeah. And if you're overfitting, then you are going to see it in your curves. But we are going to talk about this more in this chapter. Okay? So, any other question? So if you got no question, then let me just start quickly with this next chapter, and then we're going to have a short break. So what is this chapter now? I mean, this is what I call it advancement or advancing or toolbox. So what we basically want to do in this chapter, now you have the basic idea of how you can train a neural network, but now when you go in practice, you're going to see lots of things which you have not yet heard of. So I'm just going to tell you those things like, overfitting, things like what is dropout, what is regularization, and what kind of optimizer that we have in practice, and why we do use them, okay? So it might have a bit of flavor of math, but I promise it's not too much math. Yeah?
So the material that's testable for the Turing test, is it sort of the end of chapter 2? Or is
Yeah, that was the end of chapter 2, yeah.
So the end of chapter 2 is like the end of the sort of the coverage for the Turing test?
Oh, midterm test? No, you have this first part of it as well. Yeah. I'm going to tell you which part is over. But we still have 1 week, right? Yeah, so I'm going to tell you next Tuesday. Okay? So now, let's go through the optimization or optimizers, different kinds of optimizer that we use in practice. So the point is that if you get this mini batch stochastic gradient descent that I just explained for you in the previous chapter, and then you just go ahead with some serious neural network, and then you don't use PyTorch, but rather you say, okay, I'm self-confident, I want to implement everything from scratch by myself. Once you do that, you're going to see that this thing is not really working. I mean, it might work if you're very lucky, but it's not always working. And there are a bunch of reasons for that, and these are mostly, I mean, they are not too much theory. It's basically some practical issues that are going to show up when you are doing that. So the first thing I want to explain for you here is about optimizers. So basically the naive or vanilla stochastic gradient descent is still not robust and stable enough to work for us, so we need to just play around with it. So there are some tricks to make it more robust, so I'm going to talk about them. Then once we are over with that, we also want to learn how we can do hyperparameter tuning, because I told you up to this point that we are not talking about how we tune how we choose the hyperparameters, but at some point we need to learn it, right? So we are going to talk about that one as well. And then there is one tiny section of the course which we go over the idea of data. So like if you want to just get along with the next part of the course, or I mean if you want to just get a bit deeper inside machine learning, then you usually need to get the idea how people look at data in this kind of fields, areas. And then the last one is a few ideas how we can just improve. Basically, I want to talk about the batch normalization, how you can make your training faster and more robust. So let's start with the idea, the optimization part. So I want to just go over some novel ideas for optimization, so some other optimizers as people call it. And the key point is that all of them are based on a stochastic gradient descent, but they do some sort of modification to that in order to make it stable. So let's get back first to the original training problem. So what we do in training, we always have this empirical risk. So we talked about this before. We have the empirical risk, and then we are going to minimize it. And in order to do that, we are going to use gradient descent, or in reality, a stochastic gradient descent. And that weight vector, as we talked about before, is a quite large vector. So you have assignment 2. There you have close to 3,500 model parameters, learnable parameters in your model, but that is nothing pretty much. I mean, compared to what you're going to do in the next assignments. I mean, you're going to have in the order of 10 to the power 5, 6. Yeah? So this is nothing, but this is still too much. Okay? So what we're going to do, we always use the gradient descent, and of course we cannot implement it completely, so we are going to use mini batch stochastic gradient descent. And from now on, whenever I say stochastic gradient descent, I basically mean the mini batch version. Yeah? So in practice, we don't do sample level in most of them, most of examples that we have. Okay? So when I say SGD, I basically mean mini batch SGD. So now, one thing that you need to know about optimizers is the idea of convergence, or how fast they converge. What do I mean by how fast they converge? I mean, if you want to just talk about it intuitively, it means that when you start with minimizing the risk, how long it takes till you are finished with your job. Okay? This is, I mean, the faster the better, right? So this is the idea of convergence. So how long you need time in order to get your algorithm to converge. And what we talked about before was that if we choose this learning rate, the step size of the gradient descent, to be small enough, then we can guarantee that this guy is going to converge. So he's going to gradually get to a one local minimum, and it's going to stop at that point. But the question is how fast, how much time it needs. Yeah? Of course, I cannot give you the exact time, but I can give you the order of the time that it's going to take. So when you want to talk about the speed of your optimizer or optimization algorithm, you usually talk about something which we call it the optimality gap. And what is the optimality gap? You have your function. Say you have your loss function or risk function. This is your risk function. Now I am thinking about one-dimensional thing. So here is your weight, and here is your risk. And then what you do, you start with some initial weight, and you just compute gradient and move in that direction every time, right? And what you want to do, you want to get into this point, right? Now, the optimality gap is the difference between the point that you are in and the point which is optimal. Yeah? Obviously, what you do with gradient descent, you gradually reduce this optimality gap, correct? And you hopefully make it 0. This is when your gradient descent algorithm supposedly stops. So optimality gap is basically in every single iteration of your SGD algorithm. This is the difference between the risk at that point and the optimal risk. Yeah? So if you want to think of it in this naive form I draw you on the board, you can think of this guy to be the optimal guy which you want to get into, and this is where you are right now. And then the optimality gap is the gap between these two guys. All right? Now, one thing that is happening when you are doing optimization, if you choose right optimization algorithm like gradient descent, every iteration that you do, what's going to happen to this optimality gap? It's going to reduce, right? It's going to get smaller and smaller and smaller. Meaning that if you are at iteration t, having this particular difference between the 2 points, if you have this gap, then for the next iteration you're going to have smaller one, right? Because that blue point, a green point, should just move forward, and then you're going to get a gap which is smaller, right? And hopefully it's going to converge to 0, correct? Now, you start with one initial optimality gap, which could be potentially very large, and then you gradually go over, try to just reduce it, right? So now the question is that how fast this guy is going, or how fast this optimality gap is going to drop. Or in other words, how many iterations do I need to make this guy small enough? And of course, I don't want to say 0 exactly, because sometimes, for most algorithms, I cannot guarantee that it's exactly 0, but I make it as small as I want. Correct? Now, the question is how much time, how many iterations t, so if I start with iteration 0, how many iterations should I take in order to have small enough optimality gap in between my current weight and the optimal weight? Okay, so this is what we call it the convergence rate. So the idea of convergence rate is basically the speed or the amount of time that you're spending in order to get your optimality gap pretty much 0. Okay? Now, given your tired outlook, so I would give you much more break today, so 4 minutes. So we're going to have 4 minutes break, and then we start with this one. So maybe you get a bit of refresh. So, shall we go on? So, we want to just check how fast one algorithm could converge to the optimal point. So, this is the convergence speed that I told you. And mainly we want to just drop this optimality gap as fast as possible to 0, right? So the ideal scenario that you can think of is the case where we say linear convergence, and then this linear convergence, you have your optimality gap dropping with one constant, smaller than 1 obviously, in each iteration. So let's first understand what is linear convergence. So say you are in iteration t, and then you do update, yeah? You get into a new weight, yeah? Now you're looking into the difference between your new weight. So you had been here, so this was wt minus 1. Then you did one update, and then you got to wt, right? So you're getting, this is w star. This is the optimality gap that you get for your previous iteration. This new one is the optimality gap that you get for your current iteration, right? And now, of course, this guy is smaller than this one. In the ideal case is that there exists one constant alpha smaller than 1, which is always describing that guy. So you would say whatever this is smaller than alpha. I don't know what is it. What is alpha, for example, 0.9. 0.9 times this one. So it's always smaller than that one, yeah? So this is linear convergence. And if I have this property, what's going to happen? Okay? If I do one extra, at this iteration, if I want to compare it with 2 previous iterations, what is going to happen? I can write it down in this form. So I could say, okay, this guy is smaller than alpha times the optimality gap in the previous iteration, right? And then the optimality gap in the previous iteration, this one, whatever it is smaller than alpha times optimality gap in 2 previous iterations, correct? So I can say that this guy is, this blue guy, blue optimality gap, is smaller than alpha times the optimality gap in 2 previous iterations, right? Or in other words, it is alpha squared smaller than the optimality gap in 2 previous iterations. And if I keep on going backward till the very first iteration, what I can conclude that my current optimality gap is smaller than the initial optimality gap that I started with times alpha to power t. Yeah? And then all of you know that if alpha is even very tiny bit smaller than 1, this t does not need to be too large in order so that you have this alpha to power t very small, right? So even if you start with 0.99, then you're going to see very quickly 0.99 to power 2, 3, 4, and you compute that, you're going to see very quickly after 10, 12 iterations, this is going to be a very small number, right? So this is what we see. This is the ideal case, the main reason, because this is a kind of very fast, the fastest thing you can imagine, that your algorithm is just converging toward the optimal point. And if I, for example, say that this initial point is something, or initial optimality gap is something like C, so this C could be very large even, but of course this is not going to be infinity. So if I consider that C, then I could say that my optimality gap is somehow dropping by C times alpha to power t. And I don't care about a constant anything. What I would say that the order of drop is alpha to power t. Clear? You got the idea? Now, if in each iteration I am just dropping my optimality gap with a factor alpha smaller than 1, then after t iteration, I have dropped it with alpha to power t. Obvious. Okay. Now, what if I told you that speed is the amount of time I need in order to get close to the optimal point, right? Now, say that I want to get very close to this guy. So I just want to get somewhere here where this tiny bit difference is smaller than epsilon. Okay? So I want to get very close to this one, in the epsilon neighborhood of this guy. Meaning that this is the optimal point, this is the optimal point plus epsilon, so this is r star, This is r star plus epsilon. And I want to be within this area. Yeah? I want to get there. So how much time should I spend in order to get there? Okay, we do now have that the initial optimality, if the initial optimality gap was c, then our optimality gap is always smaller than c times alpha to power t, right? So if I make sure that this guy is smaller than epsilon, then definitely the true optimality gap is also smaller than epsilon, correct? Yeah? So if I start with c, I'm going to drop always. And whatever I know is that this drop, whatever it is always smaller than this guy. So if this guy is smaller than epsilon, that one, which is my optimality gap in iteration t, so my optimality gap in iteration t is the difference between r hat at wt minus r hat at point w star, right? And I do know that this guy is smaller than or equal by c alpha to power t. And if I make sure that this guy is smaller than epsilon, then I make sure that this one is also smaller than epsilon, correct? Now, I need to know how much time I need. Okay? So what I'm going to do, I'm going to take first logarithm of the both sides, correct? So I'm going to write down log of c plus log of alpha to power t to be smaller than log of epsilon, correct? Now, that t, can I take it out? Everybody's following? Can I take that t out? Yes? Okay. So I'm going to take this out, right? Okay? Now, I'm going to take this guy, put it the other side. It's going to be minus logarithm of c, correct? Now, epsilon is very small, smaller than 1, definitely, okay? Log of epsilon, is it positive or negative? Okay, so I'm going to write it down minus log of 1 over epsilon, which is positive now, right? Correct? What about alpha? Alpha is smaller than 1, right? Its logarithm, is it positive or negative? Negative. So I'm going to write it again 1 over alpha, right minus here, right? Now, if I change the sign, what should I do? Also change the direction of the inequality, right? So I'm going to change the sign and change the direction. So I'm going to write it down more. Then here it's going to be everything going to get plus, right? And then finally, I'm going to remove this guy. I put it here in the denominator. Fine? So my time, my number of iterations, should be more than this one. If I guarantee that my time is more than this one, then I can guarantee that my optimality gap is smaller than epsilon. Clear? So if I want to have my optimality gap smaller than epsilon, then my time should be larger than this one. And as I told you, this alpha, c, they're all constant. Okay, I don't care about it. The thing that I care about it is epsilon, because this is something that I am specifying, right? So I'm saying that I want to get this much close to the optimal point. Then you can compute the time, but then I tell you, okay, no. I want to get even closer. Yeah? So then you need to recalculate the time. And the only thing that you need to change here is epsilon, right? And there is some obvious relation here, because when I make epsilon smaller and smaller, what's going to happen to that time? It gets larger and larger, and it makes sense, because if you want to get very close, you need more iterations. Correct? Everybody's clear? So, now, if you look at this one, you can basically say that the amount of time that you spend is proportional to the, or is of the order of logarithm of 1 over epsilon. Okay? And this is a kind of very good convergence, or a kind of very good time that you need to spend to get that close. Okay? Because any other thing, as I'm going to show you, is going to be larger than that. Much more time you need to spend. Okay? When that happens, we're going to say that this optimizer is converging to the optimal point. It starts from one point and converges linearly into this guy. Yeah? And you might tell me, okay, there is no linearity here. It's logarithm. I mean, it's because people think of error in the exponent. So they think like epsilon is e to the power something always, and then the amount of time that you need to spend is proportional to that thing, right? And because of that, they call it linear convergence. Clear? But when you say that your optimizer is linearly converging to the optimal point, then it means that if you want to get epsilon neighborhood of the optimal point, then you need of the order of logarithm 1 over epsilon time in order to get there. And as I'm going to show you, this is quite fast. Everybody's clear what is linear convergence? Yeah? Right. Okay. So now, you might wonder, isn't that the case in practice? Isn't that we're always having like smaller gap in each iteration, and that we can always find out one factor smaller than 1, which is doing that for us? No, this is not always the case. Obviously, if you use a stochastic gradient descent, you can sometimes even go up, down, something like that, right? So there is no guarantee that your algorithm is always reducing in every single iteration. Yeah? And there is no guarantee that there exists one constant that can specify that reduction. No guarantee on that. Okay? So the only way that you could have this kind of nice property linear convergence is when your loss function, or that empirical risk, is strongly convex. This is one thing. And the other thing is that you're doing the full batch training. And you do very well know that neither of them is going to happen for you, right? So you neither do full batch training, nor your function, your empirical risk, is going to be strongly convex, because it's going to go over all of those weird ReLU different activation functions, and then you compute the cross entropy, which is going to give you a very weird function, right? So now, in realistic neural networks with stochastic gradient descent, you are not going to have this, but rather you're going to have such a property. Yeah? So your optimality gap is not dropping proportional to alpha to the power t, but it is dropping with some constant divided by number of iterations that you do times the learning rate. Okay? Now, first of all, I have told you here that this is happening when your empirical risk is a rather smooth function. Yeah? So, I mean, this is not math. Okay? This is totally not concrete statement. Yeah? But I don't want to make it complicated. I mean, if I want to be more specific, I would just define you the Lipschitz continuity and like lambda convexity, things like that. I don't want to bring that up. Basically, what I'm saying here, like for most of the losses that you know, most of the risks that you know, like it is not behaving weird. Like if you change one weight, it's not getting from -100 to +100 immediately. Okay, which is going to happen in practice. Like when you change your weights inside your neural network, your empirical risk is not changing crazy. So it's a kind of smooth function of your weights, right? But there is no guarantee that this is convex. I mean, it's definitely non-convex in practice, okay? So if this is that kind of function which we usually deal with, then we are going to have this guy. Yeah, this is the order of the optimality gap. And this L here is the Lipschitz constant, and that L is somehow proportional to the dimension of your problem, meaning that the number of weights that you have in your training problem. So the more weights you have, the larger L you would see. Okay? But all of them, as I said before, are not important. The important thing is t here, which is now in denominator. Yeah? And now let us, so basically the order is now 1 over t, and let us check what's going to happen if I want to get into epsilon neighborhood of my optimal point. So let me just write it down here. So like what we did in the previous one, we're going to say that the optimality gap, which is now bounded by t times eta, I want this guy to be smaller than epsilon, right? Now, that is quite easy thing for you, right? So you take t from here, you put t here, you change this one, right? Now, the amount of time that you are spending is proportional to 1 over epsilon, correct? This is still showing the same behavior. Smaller epsilon means larger t. Correct. But the order is totally different. Okay? So now let's check the order, for example. Say, for example, your epsilon is 10 to the power minus 3. If you have linear convergence, this is proportional to logarithm of 1 over epsilon, right? Which means that it's of order of 3. I mean, of course, it doesn't mean that exactly 3 iterations, but a scale of 3 iterations, right? But if you're talking about the sublinear case, we call this one sublinear. So in this particular case, which we have in practice, we need 1,000 iterations. Okay? So you can somehow conclude that whatever linear convergence is, if you want to get the same amount of risk, now you need around 300 more iterations to get 300 times more iterations. And this is crazy. You got the idea? So this is sublinear. It is not linear anymore. And pretty much all algorithms that we have are sublinear in convergence. But you could have different orders of sublinear. I mean, this is a bad one, 1 over epsilon. You can even have a worse one. You can even have a better one. Yeah? So you can converge faster. You can converge worse. And then the question is how we can make sure like we have at least one specific convergence speed that somehow guarantee that within feasible amount of time we are going to end our training. Clear? Any questions? No question. Great. So more of a story. If you use vanilla stochastic gradient descent that we just talked about it in the previous chapter, it is not going to work well in practice because if you really want it to let it just converge, you need to just wait forever. That's it. Yeah? It's not going to work. I mean, it's not going to work perfectly. Now, what we can do in order to get rid of that, I mean, it's a kind of, I mean, if you want to start talking about this, you can have the whole course on that, okay? Because this is basically numerical optimization. And this is the kind of thing people in like math department, in statistics department, many people, I mean, work on that. I mean, it's a field of research, people work on that. I'm not going to open up those things for you, definitely. But the thing is that I'm going to just bring you some key ideas, which you know it is used in your implementations, okay? The key ideas that we are going to talk about, the most basic one is the learning rate scheduling. So we can actually play around with this eta here to change over time, and by doing that we can improve the speed of our convergence. Yeah? This is one idea that we can do. The other thing is momentum. So we're going to see that those stochastic estimations are not perfect, and somehow we just come up with the idea of momentum to just improve them, and then based on these two ideas we could have RProp, RMSProp, or ADAM algorithm, which are the main algorithms nowadays you use in your implementations. Okay? So, now, you might ask me this question, okay, if we're not going to use a stochastic gradient descent, why you just talked so much about backpropagation? And you don't need to worry about that. Backpropagation is going to remain with us the whole semester because all of these algorithms are gradient-based. Yeah? So this is the term gradient-based optimization algorithms, meaning that at the end of the day, you need the gradient to do one step, one iteration. But how you use that computed gradient, depending on the algorithm, it's going to change. Okay? So you might simply put that gradient. You might compute something out of that gradient and then put it there. So all of those algorithms are going to use the computed gradient. The only difference is that how you use it. Okay? So backpropagation is valid in all of them. All of them need backpropagation. Clear? Good. So let's start with the learning rate scheduling idea. Any questions up to this point? I mean, I know this is too boring for 7:30 at evening, but I hope, I mean, I promise that this is one of the few. Okay. Okay, so first thing is learning rate scheduling. Okay, what is learning rate scheduling? It simply means that the initial idea that we talked about in chapter 1. So when you are doing the training, every time you modify your learning rate. So you look at what happened up to this point, and based on what you have seen, you just change your learning rate. Yeah? Because you do know that if you just take large learning rate, you're going to converge faster, but you could have the chance of just diverging. If you take a smaller, then you're going to converge, but the issue is that you're going to take more time, right? And then maybe we can play around with it. One very basic idea is that you start with one large learning rate and you gradually start to reduce it, right? So you can reduce it with different decays. These are like very basic ideas. Like you can just linearly reduce it, polynomially reduce it, or you can even exponentially reduce it. All of them gonna work, but again, these are not like very novel ideas. I mean, they are just helping you a little bit. So one other idea which is very used in practice, like in the very basic implementations, is the idea of checkpoint. Okay, so you're gonna just fix your learning rate. You just do a couple of epochs, then you test, like what we talked about in the previous chapter. You test. You're gonna see that. I mean, in the last couple of epochs, your loss is not changing anymore. Then you conclude that this learning rate is not a good one, so you're going to reduce it. Yeah? And then you again keep on doing a couple of epochs, and you check the test risk. And then if it is again getting into saturation, then you're going to drop it again, and you keep on doing till you get into the level that you want. So for example, say this guy is the test risk, this is iteration or epoch, it doesn't matter, meaning that you started training your neural network here, and each time after each epoch or after a couple of iterations, you just test it by your test data set, right? And you see that this guy is going down, 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 but at some point it's not changing that much, right? So you would say that, okay, in that learning, in that risk function, I'm getting into somewhere quite flat, right? Maybe I can jump that, right? And see whether I get smaller risk. So you're going to just, you are going down, 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 and then at some point you're not changing. So it might be the case that, I mean, you get into the flat, but you are jumping around it, right? And then one thing that you can do, you can reduce it in order to avoid jumping around it, so you just go a bit lower. So then you maybe just multiply it with this one small number, like typical choice is 0.1, and then you keep on doing more iterations, okay? And then you see again your risk is now going down, down, down. Again, you're going to stop, and at that point you again reduce that, and you keep on doing till you see no change, and then that's over, okay? So this is a checkpoint idea. It's a quite old idea. I mean, if you want to test something simple, you can still use it, but it's not that much like promising. So one thing that you can actually access in PyTorch is this learning rate scheduler. So you basically can just go over this opt-in package, which you had in your assignment 2, and then you can read learning rate scheduler, and then you can use it to do any of those things that I told you, plus lots of other things. But one key point that you should remember is that using learning rate scheduling is not essentially going to change your convergence order. It's not changing your convergence order, meaning that it's not going to change this fact that this is proportional to 1 over epsilon. It's still helping you, meaning that if with fixed learning rate you, for example, need 1,000 iteration, it could change 1,000 to, I don't know, 500, yeah, with one fixed order, fixed factor. But it's not going to essentially change anything with respect to epsilon, okay? So the order is still going to be the same sublinear order of convergence as the naive stochastic gradient descent, yeah.
I guess this is slightly far away from all this, but I was curious if you could, just because simulated annealing keeps coming into my head, I'm curious how if you could use, let's say, simulated annealing approach, especially if you're sort of converging slowly and getting stuck in local minima. Could you do something like that to maybe escape it and then?
You could do that as well, but it depends. I mean, probably after some trial, you're going to get the idea based on your test risk. So if you see that it's converging, but this is a very high test risk, then you get the idea this is not the right place that it should stop, right? Then you're going to increase it, actually, of course. Yeah, you can play that. And then you jump, maybe then you again go a bit up, and then you again start getting down, but now you get smaller. Yeah? Like, for example, if you have cross entropy, you know that you need to be somewhere around 0, right? But if you see that everything is around half, then you would say, okay, it's actually stuck in very bad local minima, so maybe I increase the learning rate, let me just jump to another point, and then that one again drops, maybe now is 0.1, and you say, okay, that's fine, maybe I can just now start reduce the learning rate to get closer and closer. Yeah? So, yeah, that was about the scheduling idea, but as I told you, scheduling is not a very novel idea. The most novel idea that we use in practice is the idea of momentum, right? Yes?
Does changing learning rate help us to pass a local minimum of finding a global minimum?
I mean, you cannot ever guarantee finding a global minimum, but you mean a better local minimum. Yeah, this is what I was trying to explain to your friend. So that one, you usually do it numerically. So look at this one. I mean, this test risk, once it starts to saturate, in practice, when you are training, you see this value of the test risk, right? Then, based on the nature of your loss function, you do know whether this is a realistic minimum or not. Yeah? So if it is, for example, a cross entropy, and you are averaging everything, you expect it to be around 0. Yeah? But then you see that this is not around 0, it is around, I don't know, 0.8. Yeah? So you would say this is not a good local minimum. Probably I am somewhere here, stuck here. Yeah? Then maybe I just increase the learning rate, I'm just converging to this one. So maybe I increase learning rate, let me jump somewhere else, and then potentially you could even jump here, which is now at higher risk, but then you keep on training, and then you see that, oh, I'm getting into, for example, 0.1, right? And then this is again probably something like this, yeah? And then you can try the same idea here as well. Yeah? So playing increasing, decreasing learning rate, it could potentially help, but you need to have some sort of intuition about the risk, right? You know that, 0.8 doesn't make sense now. It should be 0.001, okay? So maybe I increase it.
Is there any special rule for updating learning rate?
No, there is nothing. You just need to come up with some scheduling rate. And when we get into our prop, then you do it automatically. There are ideas like that. But specific scheduler, they are the ideas I told you. And you can always try it, but there is no guarantee they are, it depends on your problem, of course. Yeah. Any questions? Yeah? No, that was something else. I was talking about if you want to get out of the minimum. But here is something else. No, here I'm telling you that, here what I assume is that this is your loss, and you got into the right bowl, okay? So you want to get here, but you have one large learning rate, okay? And then what you're doing, you're just moving with that learning rate, but at some point, because your learning rate is large, you're not going further anymore. So you start just, oscillating around that one. Then you reduce it, right? And then you get closer. Again, you start to oscillate. Then you again reduce it. And you keep on going till you just get to that one. Okay? Yeah. So, any questions? Everybody's clear? So then let's go for the momentum idea. So momentum is the one which makes this stochastic gradient descent working more robustly. So what is the main idea here is that what we are computing in every single iteration of a stochastic gradient descent, as I told you, is a stochastic estimator of your true gradient, right? And then when you start, you have very bad estimation. But gradually, when you go over time, I mean, you had your previous estimations and you have your new estimations, right? So what if, instead of just using a single of them, I just use the average of the whole thing, right? This is the idea of moving average. Yeah? Anyone has heard of moving average? Yeah? So what is moving average? Say I have a bunch of variables. Oh, no. Why? Okay. This one? No? Oh, this is mine. Okay. So what is the moving average idea? Say I have a bunch of variables, a bunch of numbers. So I have x1, x2, x3, and so on till xt, and I keep on going, right? At every single time, I'm seeing one of them, okay? Now I see x1, then in the next time I see x2, so obviously I have x1 from before, and I see x2. Then I go for x at time 3, I'm going to see x3, and then I have both those two guys from before, and so on. So do you know how I compute the moving average here? So the moving average, say m is the moving average. Initially, at the very first time slot, I'm going to put it x1, right? But now, when this is what I'm going to get at time 1, or I'm going to keep it m, okay? Now, in the next time, I'm going to say, okay, it's, let me write it down here. So here is t, and t is 1, 2, 3, and so on till t, and keep on going. That at t equal by 1, what I'm going to do, I'm going to put my moving average to be x1 itself, right? Now, when I get to time 2, the thing that I'm going to do is to get m to be average of the two things that I had, right? So I can write it down. 1, say, for example, beta times x1 plus 1 minus beta x2. Okay? And you might say, well, why I put beta here, right? Because I do not necessarily want to just average it as x1 plus x2 divided by 2. Maybe I want 90% of x1, 10% of x2. Yeah? It's a kind of average, weighted average, right? But it's still a kind of averaging, right? Now, at time 3, I can do it like this. So at time t equal by 3, I could say that, I don't know, it's a beta 1 x1 plus beta 2 x2 plus 1 minus beta 1 minus beta 2 x3. It is still a kind of average between these three guys, right? But if I want to do the averaging the whole time, like every time I just get whatever I had and then average them, I need to keep all of those things, which is like a lot as time passes. This is one thing. And second thing is that I just need to do all of that computations, right? So I don't want to do that. What I do instead, I'm going to do it like this. So I'm going to say, okay, m has been initially x1. At time 2, I am going to get beta times m plus 1 minus beta times x2. The new guy times 1 minus beta plus beta times what I had from before. Yeah? M right now is exactly x1, right? And if I replace it here, this is exactly the new m that I want, right? Now, at time 3, what I do, I guess you got the idea. I'm going to get again beta, multiply it with the m that I have computed from before. So it's going to be beta times m plus 1 minus beta x3, right? Now, in every time, I'm going to get what I had from previous time. I multiply it by beta, and then I add up this new guy with factor 1 minus beta. And if I open this up, I mean, just replace everything from beginning, you're going to see again that it is a kind of weighted average of everything that I had from before. But now in each iteration, I just need to do one summation, right? And I don't need to save anything but m value itself. Now, you got the idea of moving average? Everybody's clear? Okay, so this is the idea of moving average. And what we are going to do in momentum approach is that we are going to still do a stochastic gradient descent, meaning that we are going to make mini batches and compute the gradient over those mini batches. But once we computed the gradient, we don't use exactly that sample gradient to update. We rather compute the momentum or moving average of them. Yeah? So this is going to be the stochastic gradient descent. So I have my particular weight. I compute my gradient. I just move in that direction. Now, instead of that one, I'm going to replace this g with its moving average. Meaning that at the first time I update by g, my gradient that I computed. In the second time, I update by the average of my current gradient and the previous one. In the third time, I just use my current gradient again and the average of my current gradient and whatever I had from before, and so on until the very last one. But in order to do that, I'm not going to use simple averaging. I'm going to use moving averaging, meaning that I'm going to deal with just one variable. Yes, you got a question?
So is the intuition that we're sort of removing putting less emphasis on the gradient itself?
Sorry?
By putting less emphasis on the gradient itself, we're sort of removing the variance from it?
Yes, this is the main idea. So when you do that, through time, you're just making it less variant with the estimation variance that you have.
But doesn't that necessarily make the convergence a little bit slower? Just because you are
No, I mean,
SGD, the whole point was to increase the conversion rate.
yeah, but one of the key reasons that you are seeing that convergence behavior with SGD is that you're actually, as I told you before, you're not, if you think of the whole, multidimensional loss function, if you compute a very accurate gradient, very low variance estimation, then each time you're going to get the right direction, right? And then you're going to get close to that linear convergence. But when you compute the noisy version, this is going to just shoot in different directions. So in average, it is going towards the direction that you want, but you need more iterations to just catch the average. Okay? And then when you do the moving average, you just make this variance less. The less this variance becomes, the faster it's going to be your convergence. But I guess what you are thinking of is mainly bias. It might be the bias in your mind, meaning that you would say, okay, the impact of the previous gradients is somehow getting accumulated in the current gradient. This is correct, but the fact is that when you do moving average, these coefficients here are all exponentially reducing. Like if I write this down, m here is x1, right? So I'm going to put x1 here, correct? And then the next one, I should just replace this guy here. Yeah? And then it's going to be beta squared x1 plus beta 1 minus beta x2 plus 1 minus beta x3, right? Correct? And that these guys are going to drop exponentially. Beta, when it is something smaller than 1, after a couple of iterations, it's going to disappear. The impact is pretty much not there anymore. You basically are averaging over a limited memory. Yeah, but I guess what you were saying is basically the convergence rate, isn't that? Convergence speed. Because you just spend less iterations, correct? So that's it can change the order. It definitely changes the order. Because the reason that you get from that alpha to power t into 1 over t is mainly because of that variance of your estimation. That is the main reason to make it. Okay, so now by moving average, as I told you, I simply mean that we start with some moving average, some m, and then each time we are going to look at our previous m. We multiply it with some beta between 0 and 1, and then we just add the new gradient with a factor 1 minus beta. And this moving average is something that we call it momentum. Okay? So the only difference now with the stochastic gradient descent is that instead of just replacing the gradient here, so if you look at this guy, here you are just using the gradient that you compute in the iterations to do the update. Now instead of that, you are just putting that momentum. And potentially, since momentum is just averaging over time, it is going to reduce the variation, the variance of your estimation, making it more stable, more robust, and because of that, you're getting a bit of faster convergence. You got the idea? So basically, momentum plus learning rate scheduling, these are the two key things you can do, but then there are different tricks to do that, okay? Now, if you, if you use the stochastic gradient descent, I think I have it in next slides. If you use the stochastic gradient descent implementation in PyTorch, by default it has momentum. But when you just use it simply, it's going to just deactivate momentum by setting this beta to be 0. And you can obviously see that if I set beta to be 0, this factor, if I put it to be 0, then I am going to reduce exactly to the basic version of a stochastic gradient descent. Yeah? So SGD that you have in PyTorch has momentum, but by default it is 0. Then you can just change that factor, momentum factor, to be something non-zero, and then you're going to get better convergence. Clear? Yeah, so there's one other idea I just want to mention here because you have it also in PyTorch, and I mean most, yeah, do you have a question?
Yeah, I'm not still sure what if this approach has a less variance.
Because you are averaging two random things.
Yeah, and that's going to be like the thing which we stop or mini batch and something like that.
Exactly. Because every single gradient, I mean, if you think of these guys to be the gradients, every single of them has a kind of independent noise. Yeah? When you average them, you're just reducing the variance. But doing, moving average, it could be sometimes crucial because it could lead to some sort of bias. Yeah? So you're just adding up a bit. I mean, you're getting out of the main direction. But in this, at least in particular, like naive, or say not naive, like the basic version, it's going to just show up as a constant, so it's not being a problem.
Just apply it on gradient, yeah?
Only on the gradient, exactly. Yeah. No worries. So, any questions? Great. So if you got no question, then let me just explain this nestor of momentum. So this is a kind of, say, most sophisticated version of momentum that we do. So it's basically the momentum, the basic momentum that I told you, plus a tiny bit of trick. And this is one of the things that many of you might have tried up to now when you are training or playing around with neural networks. So what does it do? I mean, this thing that you see here, it is basically the momentum approach, right? So stochastic gradient descent with momentum. You agree? So I am just going over different iterations. In each iteration, I'm going to compute momentum. And then instead of moving in the direction of the gradient, I'm just moving in the direction of momentum, right? Now, Nesterov approach suggests that maybe before we compute the momentum, or basically before we compute the gradient, maybe we can move in the direction that is already suggested by the previous momentum. Why? Because what do we know? We know that what I do know is that my next weight, which is w at time t plus 1, or w at time t, it is going to be what I had, t minus 1, minus eta times my momentum, right? And what I do know about my momentum is that this guy has one part from previous momentum, which is just one thing. Yeah, it's beta. So it's going to be beta times m t minus 1 plus 1 minus beta, my new gradient, right? This is going to be my momentum, correct? So I do not have this guy yet because I haven't computed this guy. Yeah? But the thing that I can do is that I can say, okay, what if I move in this direction? Yeah? If I move in that direction, I'm going to get w hat, right? And that W hat is potentially closer to WT as compared to WT minus 1 itself. Yeah? So the Nesterov trick is that maybe I can go ahead and compute W hat, which is like moving halfway toward my next weight, and then I compute the gradient at that point. And then I do the moving average. Clear? So once again, if I compute the momentum, my momentum is going to be my previous momentum times beta plus my gradient times 1 minus beta, right? So now, the thing that I can do, this is the basic approach, the basic momentum approach, but the thing that I can do before I start to compute the new gradient, one thing that I can do, I can already move in the direction based on my previous momentum, right? Halfway toward that, because I know that at the end of the day I'm going to move in the direction of mt minus 1 averaged with my new gradient, right? So I'm going to move halfway around towards that. I get closer to WT, and then at that point I compute the gradient, and then now I average, yeah? It might sound a bit crazy, but it's going to work, and it has a proof, yeah? So it's not like coming out of the sky, okay? So it has a proof, but I just try to explain you intuitively. So you basically, before you compute the gradient, you try to approximate the next point, and then you just compute at that point. Yeah?
So basically, when you compute gradient, you are compute the gradient at W hat.
W hat, exactly.
But you apply that gradient to W.
W, yes. Yeah, yeah, but WT minus 1, or WT, yeah, right? Yeah, exactly, because what you think is that, okay, I am at this point, this is WT, right? And then I want to get to the next point, which is WT plus 1, right? If I am doing gradient descent and I take a very long step, very long learning rate, then I have the chance of getting diverged, yeah? So I should keep it small, yeah? But given that I do know that this direction that I'm going to compute is my previous momentum, mt, plus some gradient gt, okay? So I would say, okay, I'm going to, instead of starting at this point, I'm going to start at this point and compute the gradient here. This guy is closer to that one, definitely, because I'm going to move in that direction, unless my gradient is crazy large, yeah? Unless that, I'm definitely closer to that guy. And I compute the gradient here, this is going to let me the chance to just move larger, right? So this is a kind of intuitive illustration. Yeah? But why it works, you need to go through the proof.
So basically, you move the second vector.
Yeah, this is W hat. This point is W hat. So I'm going to start from WT. I go to W hat. Now instead of G, I'm going to compute G hat. Yeah? And probably this G hat is not exactly G, but it's going to be a good estimator of that. Yeah? And then I move in that direction. Yep?
Why do we multiply the learning rate with this W hat?
Which one?
Yeah, the W hat.
Oh, I'm not sure if we should do it or not. Maybe we should. Maybe I am missing that here. I'm not 100% sure. I should double check. Probably I am missing that. It's probably a typo. This is a good point. Thanks. Yeah, but I think you're right. I need to have that eta also here. Yeah. I mean, at the end of the day, beta and eta, both of them are like parameters you're going to play around with. But I think you're right. I think if you just write it down in the form of the one which is given like in most implementation, you don't have beta here, you have some other parameter like gamma, and that gamma is basically beta times learning rate. Yeah. So now, if you go ahead and just replace this W hat into this, and then you do the math, it's going to get a bit of messy form. This is the one which when you open up any implementation, you're going to see as the form for Nesterov. But I just wanted to give you the intuitive illustration of what Nesterov is. Yeah? And again, in PyTorch, when you use SGD, you have both the momentum and you have this option to activate the Nesterov option. Yeah?
And does it always converge when we use?
Yeah, it's going to converge better. Yeah, it's going to improve your conversions.
Because we are increasing the step size. Yeah.
We're not simply increasing the step size. We are also somehow modifying the direction. Because here you are not just changing simply the, the learning rate. Basically, you are changing the direction. You are not computing your gradient exactly at the point that you were. You just go a bit forward.
Yeah.
So you are doing a sort of prediction at this point. You're going to say, okay, I'm going to get there. So I don't know exactly where it's that, but I know that if I just move a bit here in that direction, I'm going to get closer.
Okay, but for example, we can reach we can miss a local minimum or something like that. Yeah.
This one is going to reduce that chance. Because, if you fix the learning rate by doing Nesterov, you are just reducing that chance. Because as I told you, if you want to start from WT and then you want to jump to the next point, if you are too greedy and you are just taking a very large step, you can pass it. But when you just move in this direction, then what you compute is more accurate. And then because of that, you can take larger steps. So potentially you're going to reduce that chance. Yep.
I still have a question about this. So what if the gradient for the next point and the gradient for this point are different?
They're different, yes.
They are in the opposite direction, but we are updating this.
But the function that you have is probably smooth. Yeah, it's not going to show those weird behavior. You can imagine such scenarios, but in practice that never happens. As I tell you, you can never see. You can see, but that is totally unstable and impossible to train kind of neural network. That you just change a tiny bit of one weight, and then immediately, instead of giving you risk minus 100, it gives you risk plus 1,000. That is untrustable. You cannot deal with that model. Okay? So you usually, when you change those stuff, your risk is going to change just a little bit. Okay? And you also should think of everything here, this G, this W, all of them, as a kind of estimator. So you should think that everything, in the parallel world that exists, this perfect algorithm which works, but you don't have access to it. So everything that you have is a noisy version of that. And then in that case, all of these things going to make sense. Okay? So I think we are very short in time. We're over. Let me finish this last slide. So as I told you, a stochastic gradient descent in PyTorch. It has both Nesterov and momentum. Right now, if you want to just activate them for your training, you do know what they do. So you're not doing it blindly anymore. And one other thing is that this value of beta, you usually take it to be something very close to 1. And the main reason is that as the time pass, okay, I don't have it here anymore. So, but just look at it here. As the time pass, this M is going to get more and more robust and trustable, right? Because it's average over the whole time, it's going to get less and less variance. So you're going to give higher weight to that guy and less weight to the new noisy samples that you get in your training. Okay? So beta, setting it to be something around 0.9 is a very typical choice. So that's it. So we are going to start on Tuesday with RPROF. Okay, thanks.